Here is another example showing how the impulse response, step response, and overall system output relate. Let's start with h of t is this function. An impulse at 1 and a triangle, a decreasing voltage that goes from 1 volt down to 0 volts from 3 to 4 seconds. So this is delta of t minus 1 plus, now we need to give the value from 2 to 3 if we want to write this in symbolic form. We see at time equals 2 there is a sudden increase, a discontinuity in value, so we add a unit step that begins at 2, and that would, if I just had this part, that would give me our impulse plus that unit step. But now what I need to do is I need to get rid of this area here going up to time 3. So I need to subtract a ramp starting at 2. And if I did that, this would just continue down. So I need to add in a ramp starting at 3 to balance that out and get my original function that I drew. Now let's evaluate what happens, what the step response of this system is. So remember, h of t is defined such that when I put an impulse into the system, I get h of t out. It is the response to an impulse. Now, this is a linear time invariant system. It must be, or we're not, it doesn't make sense to speak about the one impulse response of the system. And integration and differentiation are both linear operations. So if I integrate the input to the system, then I have the input would be a step. So here I did integration, and I apply the step as the input to the system. Then the output the step response can be found by integrating the impulse response. So I'm using a few properties of linear time invariant systems here together, but this is a very common one. So we often, when we need to calculate the step response, we'll use this integral. And I have to use an auxiliary variable of integration there because I'm using t to represent the independent variable of time in the step response. So we could certainly work through this integral, and we will need to sometimes, but if we do this integration graphically, we can get to the answer more quickly. So if I look at h of t and I integrate it, the value is 0 up until I get to time is 1. And then at 1, I have an impulse. An impulse, one of its key defining properties, remember, is the area is 1. So when I integrate past it, I get the unit step. So, and it's delayed to the time of the impulse. So again here, if you might have remembered that the integral of the impulse is the unit step. So we're seeing that here. And there's no area being accumulated. And then starting at 2, I have this downward ramp. So I'm accumulating area of that triangle, which has base 1 second and height 1 volt. So the area is 1/2 of a volt second. And I'm going to be accumulating that area from 2 to 3 seconds. So we get up to 1.5 here. At what rate do we do that? Well, the derivative is going to be largest in the beginning, and then it's going to decay away. So we actually have a parabola like that, and it has a tangent here because we are adding 0 area as that impulse response at 3 seconds gets to 0. And then we have no more area that we're accumulating, so just like that. So to find the exact form of that parabola, we could use a few different formulas, including that we know a point on the parabola and another point on the parabola, and we know that the vertex is at t equals 3 because that is where the slope of the parabola is going to be 0. So we could certainly write that out piecewise if we wanted. So we have the value is 0 for t is less than 1. The value is 1 from t goes from 1 up to and including 2. From 2 to 3 we're going to have the parabola, and then beyond 3 we're going to have the value 1.5. Okay, now let's take a closer look at the equation of the parabolic section. So if we just start with a parabola centered at t equals 3 here, and we do a unit parabola, the expression for that parabola would be t minus 3 squared. But it has two problems. It is rising twice as fast as it should be because we want it to get up to 1/2, a change of 1/2 from the range 2 to 3, not a range of 1. So we have to divide by 2. And it's upside down. To get the green curve, we need to go upside down, and we need to shift it up by 1.5 or 3/2. So this expression here in orange is the expression of the parabolic segment that we need from 2 to 3. You could find that by integrating the function piecewise from 2 to 3, ramping down from 1 to 0. So we could do graphical integration similar to how we did graphical convolution. If we want, that would be a more direct way to evaluate it, and we would get to the same answer. So there's an expression for the curve, perfectly valid. If we simplify that and cancel out the common term, we'll get minus t squared plus 6t minus 6 over 2. And if we do a check on that, we see when t is equal to 2, we get minus 4 plus 12 minus 6 over 2. So we're just checking that it's at the right value. And that gives us 2 over 2, which is 1, as it should be, right there. And if we check the value at t equals 3, we'll get minus 9 plus 18 minus 6 over 2. So we get, in the numerator, we get 3 over 2, or 1 1/2, which is where we need to be right there. So that is our expression for the curve from 2 to 3. So minus t squared plus 6t minus 6 all over 2. And we can evaluate either expression at 2. It'll the limit from the left and the right is 1, and we can evaluate either expression, the constant 1.5 at or this expression at t equals 3. And here we have a mistake on the following line. It's just 1 1/2 is the value, or 3/2. Now that we have the step response and the impulse response, we can very quickly construct overall responses to the system without having to go through detailed calculations by using linear time invariant system properties. As an example, let's let the signal x of t be equal to an impulse that occurs at minus 2 seconds, and let it also consist of twice the step function occurring at time equals 2. So applying linear systems theory, we say we can first of all do superposition. So we have an impulse at time minus 2, so we our response will be the impulse response shifted 2 seconds earlier. We also have twice a unit step at time equals 2. Using the scaling property, the output will be twice whatever the output due just to the unit step at time equals 2 would be. And the response will be the step response, but shifted right by 2 seconds. And if we put all this together and we sketch the output function, we have, first of all, the impulse response shifted left by 2, so we have an impulse at -1, and we have a decreasing voltage from 1 volt down to 0 volts from 0 to 1 seconds. Then we have to add in twice the step response delayed by 2 seconds. So instead of starting at 1 second, it'll start at 3 seconds, and it'll step up to 2 volts instead of 1 volt because it's doubled, and it will stay there for 1 second until we get to 4 seconds. Then we'll have a parabolic section that increases by another 1 volt, and then it will stay there forever. So that would be our y of t for that particular given input, which is a sum of an impulse and a step. So the impulse response and the step response let us quickly figure out what the output looks like if the input can be represented simply as a linear combination, a superposition of impulses and steps. As we get to more advanced techniques in the class, we'll be able to handle sinusoids, periodic functions, and non-periodic functions in the input.